Hello, thank you for being here today. I'm Sonia ABDELLATIF and I will present the paper entitled New High Efficiency Heater Design for a 3-axis CMOS MEMS Convective Accelerometer, co-authored together with Brahim Mzghani, Frédéric Mailly and Pascal Nouet. So to go through this presentation, we are going to start with an introduction in which we will cite the problematic and the proposed solution, the proposed heater design, the FEM model that we have used for simulations, and the optimization of the design. After that, we are going to compare the output of the proposed design with another design found in literature. Next, we are going to explain the implementation of the heater in CMOS technology, and we will finish with a conclusion. Now, the problem with tri-axis convective accelerometer is that they often have tridimensional, complicated, and uncompact structures, making them not suitable for conventional fabrication process. So we have one possibility. It is to use in-plane detectors for out-of-plane sensing. This offers the possibility to implement a 3-axis CMOS convective accelerometer. However, the out-of-plane sensitivity in this case is very low. In this work, we propose and optimize a new heater design to improve sensitivity and efficiency without sacrificing CMOS compatibility, with efficiency being the ratio of sensitivity over consumed power. Now, the design is developed using a 0.35 micrometer CMOS technology associated to a front-side bulk micromachining post-process, leading to a monolithic solution of a 3-axis convective accelerometer. Now, before jumping to the next section, I would like to explain how convective accelerometer work. The accelerometer is composed of a cavity obtained using a front-side bulk micromachining. Above the cavity, there is a suspended heater in the middle, and temperature detectors are symmetrically distributed around the heater. When the heating resistance is supplied with electrical current, it heats up the surrounding air or any other liquid or gas to create a symmetrical temperature distribution. Therefore, the detectors measure the same temperature. The presence of an acceleration changes the initial shape of the thermal bubble around the heater. For example, when a lateral acceleration is applied, the hot bubble is shifted towards the left in case of a positive acceleration and towards the right in case of a negative acceleration. Now, when a vertical acceleration is applied, the heat bubble tends to stretch when the acceleration is positive and to flatten when the acceleration is negative. Therefore, the average temperature of the same sensors used for in-plane measurement changes. The temperature difference is then read out using a convenient conditioning circuit. The design that we have proposed consists of a square-shaped heater with 4 centered heating zones. Here are the heating zones. Using 4 heaters at the corners of the heater only is supposed to reduce power consumption. A hole is introduced in the middle of the heater to improve the etching time. And 4 optimized Y-shaped beams achieving best sensitivity values due to the reduced surface are implemented. This design allows the heater to be enlarged in the cavity and as a result create a bigger hot bubble which enhances the sensor sensitivity. Now, for the finite element modeling, we have developed a model that combines an SU2 suspended frame, poly-H resistors and their aluminum connecting wires passing through the attachment bridges, an air volume representing the etched cavity and the sensor package. As for boundary conditions, a voltage is applied at the extremities of 2 opposite wires, whilst the others are grounded, and a temperature of 300 Kelvin is set on the surface of the top and bottom cavities. The modules we have used for simulations are Joule heating, used to raise the heater temperature according to the applied power, heat transfer, modeling the convection phenomena, and laminar flow, used to model the acceleration effect. Now, the 3D FEM model that we have developed takes in consideration the overall heat losses and exchanges, including the heat losses along connection wires and the implemented resistance. As for the design optimization, we aim to create a structure that is compatible with a standard 0.35 micrometer CMOS technology process, followed by a front-side bulk micromachining etching step. Two rules have to be considered. The minimal width of all suspended structure is 25 micrometers, and the minimum distance allowed between two suspended structure is 35 micrometers. With these parameters being set, the distance between the microheaters L goes from 80 to 150 micrometers, and the wings width W2 is accordingly goes from 25 to 73 micrometers. This optimization consists in minimizing the power consumption while retaining high performance in terms of sensitivity. Here we present in-plane sensitivity as a function of power for different values of the distance L. From these results, we can say that when L is inferior to 100 micrometers, the heater size is not sufficient. When L is superior to 100 micrometers, the distance between the heaters is too large, and the best sensitivity values are obtained when L is 100 micrometers. The same results are found for out-of-plane sensitivities. To understand the effect of the geometrical parameter L on sensitivity, it is important to know that the sensitivity is highly affected by the hot bubble initial size. The larger the bubble, the higher the sensitivity. The isotherms produced by the heater are largely affected by the distance between the heat and resistances. When L is 100 micrometers, the isotherms produced by each of the microheaters are combined, generating a single hot bubble. However, when L is 115 micrometers, the distance between the microheaters prevents the fusion of the produced bubbles. In terms of efficiency, the same results are found for both in-plane and out-of-plane sensitivities, and the optimal L value seems to be 100 micrometers. Here we present etching simulations of the optimized heater design. Simulations confirms that the structure can be fully released within an acceptable etching time, about 3 to 4 hours. This is mainly due to the hole introduced in the middle of the heater, and also to the orientation of the heater at 45 degrees. Next, we aim to compare the new heater design results with a reported tri-axis CMOS accelerometer having a spiderweb structure. As we can see, for in-plane acceleration, sensitivities obtained with the new design are always higher than the spiderweb design. Sensitivities obtained with a power consumption of 9 mW using the spiderweb structure can be obtained with less than 7 mW using the new design. Maximum sensitivities of about 257 mK per J for the new design versus 66 mK per J for the spiderweb design. Improvements of 60% is observed at equivalent power consumption. As for out-of-plane accelerations, the new design offers improved out-of-plane sensitivities, with a maximum sensitivity of about 20.2 mK per J for the optimized structure versus 3.4 mK per J for the spiderweb structure. An improvement of 113% is observed at equivalent power consumption. The heating temperature of the proposed heater is also different. In fact, for a given power, the maximum temperature observed in the new heater is strongly reduced. This gives the possibility to significantly increase the sensitivity without any risk of thermal-induced damages. The maximum power accepted by the new design is 17 mW for a heating temperature of around 700 Kelvin, which corresponds to the maximum temperature allowed before device failure versus 9 mW in the spiderweb design. In terms of efficiency, the proposed design overperforms the classical one. Maximum efficiency is up to 15.1 millikelvin per J per milliwatt for in-plane accelerations. Whereas for out-of-plane acceleration, the gain in terms of efficiency is even greater, and the maximum is up to 1.2 millikelvin per J per milliwatt. A layout of the sensor was designed based on the CMOS 0.35 micrometers technology design rules and specifications. For the heating resistances, 4 resistance of 1 kilo ohm are implemented, and the material chosen was highly resistive polysilicon due to its high sheet resistance. This allows the implementation of a high resistance in a reduced surface. The resistances are connected in a parallel configuration. Although the parallel configuration is more power consuming than serial connection, but it allows a symmetrical distribution of the temperature in the heater. For temperature sensing, 4 poly-1 temperature sensing resistance of 400 ohm are also implemented next to the heater resistances. The resistances are connected in serial to measure the heater temperature. According to simulations, and for a maximum heating temperature of about 700 Kelvin, the consumed power is 17 milliwatt. The voltage needed for supply is 2.57 volt, and a total current of 6.4 milliampere will be divided to supply 4 heaters. To conclude, a new fully CMOS compatible heater design for a convective 3-axis MEMS accelerometer is proposed. The heater design is optimized with focus on the CMOS 0.35 micrometer technology to achieve best results in terms of sensitivity while reducing power consumption. Maximal in-plane and out-of-plane sensitivities of 257 millikelvin per J and 20.2 millikelvin per J have been observed for a maximal temperature of 700 Kelvin. The proposed accelerometer is able to operate in a large range of input power due to its higher efficiency. The layout of the new design has been detailed for future fabrication using CMOS technology followed by a post-process MEMS etching step. This concludes my presentation. Thank you for your attention.